Is everybody ready for an astronomy lesson? This will be the second largest class I've taught. The first one I'll talk to you about today. I've titled the talk 121 seconds because that's how long the eclipse lasted at Furman. Well, let me get into it a little bit more. What else can happen in 121 seconds? Well, let's think. I can make a bowl of oatmeal. I can pop a bag of popcorn. On a more nerdy side, you can actually bounce radar from the Earth to Venus at the speed of light, and it takes about 2 minutes. Yeah. Of course, there are certainly things that are much shorter lived. For example, 121 seconds is an eternity to a Higgs boson in the Large Hadron Collider before it disappears in a puff of subatomic particles. It was very difficult to find that object because it didn't last very long. But 121 seconds is nothing compared to basically the breadth of time and space of our universe. This image represents an echo of the Big Bang, which heralded the beginning of the universe 14 billion years ago. What 121 seconds means to me, and what it meant for all of us that were around that very hot summer day on August 21st, 2017, was that was the day of the Great American Solar Eclipse. It was a coast-to-coast solar eclipse that traveled, that basically the shadow of the moon went from basically the Pacific coast in Oregon across the United States to the Atlantic coast in Charleston. It took only 90 minutes to cross the United States. But the thing is, it crossed right over Furman, and we knew it was going to cross over Furman years ago. I was employed in 1999, and I knew it was going to be here. I'm going to talk a little bit about how I knew that. Well, the thing is, there's many steps that have to happen for an eclipse to happen. And among those, one, you have to have an alignment of the sun, the moon, and the earth, a syzygy, they call it, in which basically the moon shadow strikes the earth. But that can only happen every once in a while. The moon's orbit's tilted with respect to the orbit of the sun, of the earth around the sun, by about 5 degrees. So we don't get eclipses every month. We don't get a solar eclipse every month. We don't get a lunar eclipse every month because it misses. The shadows miss all the time. But there are two places in these orbital conjunctions that can occur. They're called nodes. And if the moon happens to be new phase on one of these nodes, you get a solar eclipse. The second thing that has to happen is, well, the shadow actually has to reach the Earth. And the moon's orbit's not circular. It's elliptical. Sometimes it's a little closer, sometimes a little bit further away. You've probably heard of supermoons. And that's when the moon's a little bit closer to Earth. Well, if the moon's too far, its shadow can't actually touch the Earth. And you end up getting a different kind of apparition. You get what's called an annular eclipse, where a ring of sunlight ends up going around the moon. And I've actually seen one of these. They were quite nice, but I've never actually saw a total eclipse until last year. The third thing is you have to be at the right place at the right time. Now, for those of us who are fortunate to live underneath the eclipse path or have the means to actually travel to it, that's great. You actually get to see an amazing thing. And for most Americans, 100 million people could actually drive and get to see one of these. That's why we call it the Great American Solar Eclipse. The shadow itself is only 70 miles across. So if you're here in Greenville, you got to see it for 121 seconds. If you happen to be in, say, the Anderson jockey lot, you get to see it for 158 seconds. And the shadow itself is traveling across the United States. 90 minutes across the United States means it's moving at 2,200 miles per hour. That's faster than any commercial aircraft. I can only think of one aircraft in history that's actually been able to go that fast. It was a spy plane that they have discontinued. The Blackbird. Well, because we knew this eclipse was happening at Furman, we at Furman hosted an event called Eclipse at Furman. And we didn't know how many people were going to come. but we were really amazed at how many did. So we had, on that day, parents, students, which, by the way, was move-in day for a lot of upperclassmen. That was chaos in its purest form. Of course, we had faculty and staff, and we had visitors from the Greenville community. We even had visitors from as far away as Scotland. I met a man from Scotland, and I met a man from Japan. People come to these things. We have eclipse junkies that try to go to every one of these things. And of course, when we were planning this, we had to make sure that everybody had a pair of these. And there's a reason why, because people are really scared of eclipses. When I was a child, they wouldn't let us go out and look at an eclipse because you'll burn your eyes out. Well, we solved that problem. Everybody got a pair of glasses. We also gave everybody a glass of water because it was like in the 90s that day. It was really hot. Of course, the glasses came in handy. Everybody's standing in the stands watching the eclipse happen. And of course, people breaking out their cell phones. You know how hard it is to take a picture of the sun with your cell phone? Even harder when you're trying to take it through one of those glasses. I know I tried. But there was an even better way to watch this. You didn't even have to look up. You could look down. If you were sitting under a tree, and as the eclipse progressed, as partial went to total, you could actually watch sun filtering through leaves and trees and making tiny images of the sun on the surface, on the ground below, because each leaf acts like a pinhole camera, or a camera obscura, as they used to call them. It makes an image of the sun underneath. It's a really cool way to watch it. Of course, I started off the day by setting up a small telescope outside the stadium. And as the day progressed, we had more and more people show up. In total, we had about 14,000 people come to our event. And it was totally free. It's not like Clemson that charged $50 for tailgazing spots. We wanted the community to share this experience with us for free. It was great publicity, too. But my first view of the eclipse started about 1:09 p.m. The telescope I had set up just projected sun onto a board so that other people in the people standing outside the stadium could actually watch it progress. Didn't have to look at a TV screen, didn't have to use their glasses. At about the same time that I set this up, notice on the image on the right, what is it that's there on my shoulder? A cicada flew on and landed on me and stayed with me for a while. The poor little guy was actually confused. As the sun began to be blocked by the moon, it got confused and it just flew around erratically and landed on me and stuck around for a while. I thought that was pretty cool. Just up the road in Jocassee Gorges, a friend and local teacher by the name of Weinberg, he actually asked me if I had a solar filter he could borrow to take pictures of the sun, and I let him borrow one. And he took these amazing photos of the eclipse, starting from first contact when the moon's shadow begins to cross over until we reach totality. Those are amazing pictures. I couldn't take any. I was stuck emceeing the event at the stadium. I'm an astronomer. I wanted to do that. But I also wanted to share the science with the people. Now, in the stands, we had some dedicated students and others in the stands who actually wanted to capture the day. In fact, these are images taken by one of our physics majors, Ray Garner. He actually captured the approach of the moon's shadow. See, if you're at high altitude, you can actually see the shadow going across the Earth's surface. But if you're on the ground, you really can't tell until it starts getting darker. And so he actually captured, you just go from the top left, bottom, and then to the right. You can actually watch the shadow come. And how you know it's there is, sure, the sky's getting darker, but notice the clouds are getting darker at a distance. Of course, my favorite, and this is one that the people over in marketing actually gave me a couple of days ago. This is a video showing the eclipse, time-lapse photography. Isn't that crazy? Here, you want to watch it again? Because when this was happening, the sun was being blocked by the moon, the temperatures were cooling off, and right as totality began to start, the cicadas and the crickets in the woods behind the stadium began to sing. And if you were out and around the lake, you probably noticed the same thing. I had a friend of mine, Mike Spec, who teaches in education here. He actually had a thermometer set up to a computer. He actually watched the temperature drop by 8 degrees when it reached totality. Isn't that amazing? Of course, the pictures that follow are just spectacular because when totality happened at roughly 2:38 that afternoon, the crowds that were cheering it on, all of a sudden they just became hushed and quiet, silent. We were all watching. Time stood still for us for 121 seconds. And we look up, we look around, and everything was twilight all around. And we look up and we see things that you normally can't see in daylight skies. You can't see the corona of the sun. You can only see it during an eclipse or from a spacecraft. You can't see stars in the daytime by eye, but here's a picture, another one by Ray. You can actually see the star Regulus right next to the sun. Of course, the most amazing photograph of all is one that I wanted to take, but I'm glad somebody else did take. This is taken by a professor named Muller, who was out west taking this image. You actually see the corona basically in its glory. These tendrils of light following the sun's magnetic field, extending from the surface of the sun all the way out into space. And if you look along the edges very carefully, you can actually see tiny little bits of pink light. That's actually hot hydrogen gas floating above the surface of the sun. These are things we call prominences that float above the sun's surface, trapped by the magnetic fields of the sun. And there's one thing you might notice, that on that day when you look by eye, the moon was perfectly dark when you looked at it by eye. But if you take a picture, you can actually see the surface of the moon. Where the heck is the moon? Where's the light coming from? It's reflecting off the Earth's surface back onto the moon during the eclipse. So that's Earth shine that you're looking at right there in that image. So for us, time stood still for 121 seconds as we enjoyed this momentous, awe-inspiring eclipse. There's tons of pictures. You probably have some of your own. But of course, there's photographers everywhere that took so many more, much better than what we could ever do. But again, it's that moment when the eclipse ended that was also just as exciting, because as soon as it ended, we're actually witnessing sunrise on the moon's surface. The moon itself had been blocking the sun for 121 seconds. All of a sudden, the sun will rise up through a valley or a crater, and you'll get a very tiny bit of light on one side, more so than the others. We call those Bailey's beads. But then, as more and more light appears around the edge of the moon, you actually see something that looks like a diamond ring hanging in the sky. We call this the diamond ring effect. It's absolutely, it's beautiful, and it only lasts for a second, and then it's gone. And that's the thing. The whole thing was over. And you get that sense that I just saw something really, it's awesome and spiritual. And it actually made me cry that day. 7,000 people in the stands, and I'm the one down the field crying. Never seen one before. But it hooks you because you want to see another one. You want to see another one. And the thing is, you go, okay, well, where's the next one? Can I get to it? Because we're not due for another one here in Greenville for a very long time. So maybe we can drive to the next one. Well, how do you find them? How do you find out when and where to go? Well, what you do is you just Google NASA Eclipse. It'll take you, one of the top links you'll find is the NASA Eclipse website. And you can navigate around and find eclipses that have happened in the past and into the future for a millennium. That's some really cool stuff, because that means they've gone through and modeled the solar system's motions, the sun, the moon, the earth, all of that, and using a computer actually predicted when these things are going to occur and where they're going to be, where they're going to occur on Earth. So if you navigate around, you can find a place where here's the eclipses between 2021 and 2040. Look for the United States. Do you see a blue line or a blue curve going across it? That blue curve is the next one in the United States. Well, there's a red curve. That's an annual eclipse. I'm not going to count that one. Sorry. I want to see a total one. But the blue one, that's going to happen in 2024. It's going to cut through Mexico, through Texas, the Midwest, through western New York, Maine, into Canada, and then gone. It's going to last a little bit longer than the one we just observed last year. I'm certainly going to drive to that one. I don't care if there's classes or not. The dean's here, I'm sure, and he probably heard that. But that's not the next one. The next one's actually somewhere else. We have to leave our part of the world and move to another part of the world in order to see the next one. In fact, the next one is going to be in 2019. That's just next year. And it's going to be in South America. Look at South America, and you'll notice there are actually 2 or 3 blue lines crossing that continent down at the very bottom. In 2019, you'll have one that crosses from Chile into Argentina and ends in Buenos Aires. And in 2020, there's another one. Not even a year later, another one. These people are so lucky they get to see 2 within driving distance in a year's time. And you get to see another one in 2020. Now I have to wonder, I am Furman's only astronomy professor. I wonder if they would allow me to sponsor me for a trip down there. If you continue navigating that site, you'll notice it also predicts lunar eclipses. We had a lunar eclipse 2.5 weeks ago. Did you know that? You probably don't remember the eclipse, but you probably remember the moniker super blue blood moon. Do you remember that? It was in the news very briefly. But the thing is, it was another eclipse. Less than a year after the solar eclipse in August, we had one 2.5 weeks ago, and it looked kind of like that from here at Furman. I took this picture. A couple of students and I were brave the cold. It was in the 20s. It's 6 in the morning. We're just down above the playing fields, above the track, just down the road from this building. And we took these pictures and witnessed another eclipse. Super, because it's close to the Earth. Remember the ellipticity of the moon's orbit? It's closer to the Earth. It looks bigger. It's blue because it's the second full moon of the month. And then blood because that's the color the moon turns when there's a lunar eclipse. So now, for the last sort of 121 seconds remaining of my talk here, I want to talk a little bit about the history of eclipses, just briefly. The thing is, would it surprise you to know that we've been able to predict these things for over 2,000 years? Now you know that the NASA Eclipse website didn't exist that long ago. We didn't have computers. There were no laws of physics. But there were a lot of clever astronomers, people who watched the skies. But then you have to wonder, how could they have predicted when eclipses occur when you look at that map right there, that's 20 years worth of eclipses, and you look at any one particular place, you don't necessarily get an eclipse for years or even generations from one instance to the next. And they're hundreds, if not thousands of miles separated by distance on land. So how could they have predicted when solar eclipses occurred? We have to go back to almost the very first panel I showed you. There's 2 sets of alignments that are possible. One, sun, moon, earth. The other, sun, earth, moon, which is what results, which is what results in a lunar eclipse. They share the same patterns in time. And these ancient Greek astronomers over 2,000 years ago actually figured out the pattern. Because it turns out that when the moon comes into the Earth's shadow, at totality, everyone on the nighttime side of the Earth, no matter where you are, can see that lunar eclipse. And so over the years, decades, centuries, they recorded the instance of all of these lunar eclipses and, of course, solar eclipses, and found a pattern. In a period of time of about 223 lunar months, cycles of the moon going around the Earth, you get the same eclipse. We call that a Saros cycle. It actually takes a few Saros cycles for that eclipse to come right back to your location on Earth. It'll appear somewhere else. And there's multiples of these cycles occurring at any given time. Each one of these represents a different Saros cycle. And if you wait three Saros cycles, you'll see this map replicated again in time. That's really powerful considering you have people who have no computers and no concept of laws of physics. But they had eyes and they had brains. And they were very clever. Now, they of course, felt that the Earth was the center of the universe and measured everything as if everything were going around the Earth, the sun, the moon, the planets, and so on. They even built a machine, what we consider one of the earliest mechanical computers. This was a machine, the Antikythera Mechanism, was found in a shipwreck in 1902. It was actually, after some studies over the years, we found out to be a very complex machine that you turn a crank. It acts like an astronomical calendar and computer. You can actually make the planets and the moon and the sun go around and around. And on the backside is a little dial indicating when the next eclipse occurred. There wasn't a machine of this like made anytime between that time period and the end of the Middle Ages. And speaking of that, that's science. That's science, being able to predict or model something and then it be repeated over time and again, being able to predict events as they occur. That's science, even though the scientific method didn't really exist. But 15 centuries later, notable scientists like Copernicus, Kepler, and Galileo, who you may have heard of, these people actually studied and actually observed and found evidence that it wasn't the Earth at the center of the motion, it was the sun. They challenged the ancient Greek models. It was sort of an astronomical revolution, which really is a great example of how the scientific method works and how science evolves over time. Because, in essence, science builds on the observations of previous observations. Basically, the goal is the same, the pursuit of truth. Politicians, yeah, maybe you know where I'm going with this. Some politicians, not all, kind of deny the science that we're actually teaching our students. But you can't deny an eclipse. We all came together on that day in August last year to observe, to witness the great American solar eclipse. We got to witness the power, the predictive power of science, that it wasn't harmful to the mind and body, especially if you had a pair of these. And last, it doesn't have to be an eclipse that brings us all together. I'm happy to say that a few weeks ago, we also witnessed another event. You might remember this. Kudos to Elon Musk for sharing his love of science and for using it to actually blaze a trail. He really wants to go to Mars, but I think we're going to go beyond Mars. Thank you.